Okay, hello everyone. I'm going to go ahead and record this lesson, so hopefully you can figure out what's going on. So we're going to start with end behavior of a polynomial function. So in math, this little arrow symbol, this one right here, this little arrow that I drew, what that means is approaches. So when x is approaching negative infinity, if we think about a graph, if x is approaching negative infinity, that's going this direction. So it's referring to the left side of our graph. However, as x approaches infinity, as it's going in the positive direction, we're headed that direction. So that's to the right. Now, if we're saying the limit as x goes to negative infinity, f of x is the value that f of x approaches, on the left side of the graph. So remember that f of x is just a fancy way to say y. So the limit as x goes to negative infinity is saying that as we go to the left, what is our y value doing? Whereas the limit when x goes to infinity is what is our y value? Oh, I spelled approaches wrong. On the right side of our graph. And again, to the right is as x is going to infinity, to the left is as x is going to negative infinity, right? Because we're going negative directions on the left side, positive directions on the right. So if the graph is going up, so if we're headed in this direction, we're headed towards a positive infinity, right? Because on a graph, these are the positive directions. Now, if our graph was going down, we're headed towards negative infinity in the y direction. So we're going to use this in order to write what we call our end behavior. So the first thing we're going to do is we're going to plot our quadratic graph. So we're plotting y equals x squared, which should look like this. Right, this is our parent function of a quadratic, also known as a parabola. And we've been working on these pretty consistently. So it says, what is the end behavior of a function when the leading coefficient is positive and the degree is even? So that's what's happening here. The leading coefficient, the number out front, is positive and the degree is even. So it's saying as x goes to negative infinity, again, that's on the left side of our graph. So that's happening right here. Our graph is going up. So because it's going up, it's going to infinity. And then it says, as x is going to negative infinity, as x is going to positive infinity, which is on the right side of our graph. Again, our graph is also going up. So our graph would again be going to infinity. And so that is how we would write the end behavior. Okay. So let's say, what if I had y equals a negative x squared? So our leading coefficient in this one is a -1, and our degree is a +2. So there is a negative leading coefficient, and our degree is even. So if I plotted this, this would be that parent function, but reflected over the x-axis. So it's going to look like this. Okay. So we would say as x is going to negative infinity, again, that's on the left side. So that's happening here. This time we're going down. And so because we're going down, we're actually going towards negative infinity. And then we check as x is going to infinity, that's on the right side. And again, we're going down. So those match. So they're both going to negative infinity. Okay. So looking at number 3, this time our leading coefficient is back to a +1. And our degree this time, our exponent, that's what the degree is 3. Okay, so if we graphed this, it's actually going to look like, oh, that goes off of our graph, but it would be -2, 8. So it's going to look something like this. And so we say as x goes to negative infinity, that's going in this direction. So that's on the left side. Our graph this time is going down. So that means it's going to negative infinity. As x goes in the positive direction, that means it's going to the right because that's our positive numbers. This time our graph is going up, so it's also going in the positive direction. So that would be to infinity. Okay. Now, if we had a negative leading coefficient, which in this case we do, our leading coefficient, the number out front is a -1, and our degree is 3. Okay, that's the exponent. Our graph would look something like this. Okay, and so as x is going to negative infinity, so on the left side, our graph is going up. So our graph is going into infinity. And as x is going to positive infinity, so going to the right, our graph is going down, so it's going to negative infinity. Okay, if you're struggling with the infinities a little bit, one thing that may help you is x going to negative infinity, that means left. X going to a positive infinity, that means right. F of x, that limit as x approaches whatever, when that's equal to a positive infinity, that means up. And that limit as going, when it's negative infinity, that means down. So as always, right and up are our positive directions. Left and down are our negative directions. And we wrote all of this up here. This is just it kind of written in one little block. So if that helps you, you can use that. But hopefully we've started to notice a pattern that's occurring here with these graphs. And so we should notice that there are 4 different things that can happen. We can have something that is has a positive leading coefficient. That's what I mean. Positive LC means positive leading coefficient or a negative leading coefficient. And we can have an even degree, or we can have an odd degree. So looking back, the first one we had was when we had a positive leading coefficient and a positive, or I'm sorry, and an even exponent. And so we would have a positive leading coefficient and a even degree. And so what's happening there is both sides of our graph are going up. So whether they're positive or negative, our graph is going up. So that has our right side going up and our left side going up. Okay, and so the way that we would write this is limit as x goes to negative infinity. That's our left side. It's going up. And the limit as x goes to positive infinity, that's our right side. It's also going up. Now, if we had a negative leading coefficient and an even degree, that's what was happening in our second one. We had negative leading coefficient, even degree. Both sides of our graph are going down. And so our right side was going down and our left side was going down. So again, we would write this as the limit as x goes to negative infinity. Our graph goes to a negative infinity. And the limit as x goes to positive infinity, which is our right side, our graph is again going to negative infinity. So hopefully we notice that when we have an even degree, both our right and our left sides will be doing the same thing. So if our graph is positive, so if we have an even degree, both sides should be doing the same thing. Now, what if we had a positive leading coefficient and an odd degree? Okay, so that is what's happening in number 3. We have a positive leading coefficient and an odd degree. And we should see that this time our right side is going up and our left side is going down. So we would write that as the limit as we go to negative infinity. As x approaches negative infinity, f of x approaches a negative infinity as well, because that's our left side and it's going down. Our limit as x is going to a positive infinity, as x approaches positive infinity, f of x approaches a positive infinity because our right side is going up. So hopefully we notice that if we have a positive leading coefficient, our right side is going up both times. And then finally, in number 4, if we have a negative leading coefficient and an odd degree, our right side was going down and our left side was going up. So the limit as we go to the left, so negative infinity, our graph is going to a positive infinity. And the limit as we go to the right is a negative infinity. So things we should notice. If something is even, the right and the left do the same thing. If something is odd, the right side and the left side do the opposite. Okay, so even they're doing the same, odd they're doing the opposite. If something has a positive leading coefficient, the right side is always going up. And if something has a negative leading coefficient, the right side is always going down. So that can kind of help us determine in the future. So positive, right side goes up, negative, right side goes down, even degree, left is going to match the right, odd degree, left is going to do the opposite of the right. So it all kind of depends on the right. Okay, so moving on. So standard form is when a polynomial function is written with exponents in descending order. So it must be in standard form in order to determine the leading term and degree. So that's like saying we have to have x to the third, x squared, x, and then our constant. So we have to have descending order of those exponents. Okay, the leading term is a term with the highest exponents after you multiply all the factors together. So once you get it in standard form, then you can determine your leading term. You only need to multiply the x terms of each factor together. So, sorry, that was a little confusing. So what I mean by that is if I have 2x plus 1 times, say, x plus 2, all I need to do is take my x terms, multiply those two together, and my leading term will be 2x squared. Okay, so we don't have to distribute this whole thing out in order to get our end behavior. Okay, so moving on to number 1, I want to get standard form of this. So I need to start by rewriting it. So I'm going to put the x squared term in first. So 2x squared, make sure those addition or subtraction signs are kind of stuck to them. Then I would take my x term, so minus 3x, and my constant minus 1. So in this case, that first term, that 2x squared, is going to be my leading term. So I have a degree of 2, right? That's my highest exponent. So I have a positive leading coefficient. Hopefully we see that. My leading coefficient is positive. And so that means my right side is going up. And my degree is even. So that means my left is going to match my right. So the limit as x goes to negative infinity, so as we're going to the left, our graph is going up, so it's going to a positive infinity. And the limit as as x approaches infinity, we're still going up on that right side, so we're still going to infinity. Okay, and so those would be our limits there. Okay, so in standard form for this second one, again, highest degree this time is a negative 2x to the 7th. The next highest would be that 4x to the 4th. And then the last one would be that 3x squared. You do not need to factor it out, do anything like that. We're just trying to get it in standard form. My leading term is going to be that negative 2x to the 7th. And so my degree should be 7 because that's that highest exponent. So looking at this, my leading coefficient is negative. That means my right side is going down. And my degree is odd. So that means my left is doing the opposite and it's going to go up. So as x approaches negative infinity, so as we're going to the left, our graph is going to go up. So it's approaching infinity. And as x goes to infinity, our graph is going to go down, right? Because that's the right side, it's going down. So it's approaching negative infinity. The nice thing about number 3 is it's actually already in standard form. And our leading term is in negative 7x squared with our degree, that exponent being just 2. So for this one, my leading coefficient is telling me that my right side is going down because it's negative. And then my degree is even, so my left should be matching my right. So as x is going to negative infinity, as it's going to the left, our graph is approaching negative infinity. And as x approaches infinity, as we're going to the right, our graph is approaching a negative infinity as well. And that would be our end behavior. Now, what if I have something written like this? So we want to find the leading term of the function and then describe the end behavior using our limits. And we can check our answers with a calculator. For the sake of time, I'm not going to check my answers with a calculator, but you can if you would like to. And so the first thing we should see here is what is the highest degree each of these factors is giving us. So in this first one, we have a negative 2x, okay? That is the highest degree exponent from this first term. From the second term, the highest degree exponent is just an x. From the third term, the highest degree exponent of our variable is again just an x. And from the fourth term, it's going to be an x squared because of this squared on the outside. So I'm taking those highest degree exponents and I'm multiplying them all together. So that will give me negative 2, okay, because that's the only coefficient I have. X times x times x is x to the third times x to the second is going to be x to the fifth. Okay, so that's what I'm trying to find. So the way I do that is just by taking the highest degree of each one of those factors and multiplying them out. We're not going to distribute the whole thing out. We don't need to do that. That's doing entirely too much. And my degree here is going to be 5 because I'm taking the degree of that leading term. So this one is negative, has a negative leading coefficient. So that's telling me that my right side should be going down. But it has an odd degree. So that tells me my left is doing the opposite of my right and it's going to go up. So my limit as x approaches negative infinity, that's on the left side. So that means my graph is going to infinity. And my limit as x approaches infinity, that's going to be on my right side and it's going down. So it's going to negative infinity. Okay, so similarly with number 5, in our first term, we have an x squared. In our second term, the highest thing we could get is an x to the third. And in our third term, the highest degree we can get is an x squared. Okay, so I'll multiply all those together to get that my leading term is going to be x to the 2/47th, right? Because I'm adding all those exponents together. Because x to the second times x to the third times x to the second is x to the 7th. And so my degree is 7. So this is positive, meaning that my right side is going up. And it's odd, so my left side is doing the opposite of that, so it's going to go down. So as x approaches negative infinity, as we go to the left, f of x is approaching negative infinity because we're going down. As x approaches infinity, so as we're going to the right, f of x is approaching infinity because we're going up. Okay, moving on. So, So looking at number 6, I'm going to take that entire first term, including that negative. So that'll be negative x to the 4th. And then I'm going to look at my second term. Okay, the highest exponent I could get here is just a regular x to the 1st. And then looking at my third term, the highest exponent I can get here is an x to the 5th. Okay, and when I multiply all those together, I'm going to get negative x to the 10th. So my degree is 10. Because negative x to the 4th times x to the 5th is negative x to the 10th. So it's negative, so that means my right side is going down. And it's even, so that means my left side is going to match my right. So as x is going to negative infinity, f of x should be going to negative infinity as well. As x approaches infinity, or as it goes to the right side, my graph is still going down, so it's still approaching negative infinity. Okay. Looking at number 7, the highest degree in my first term is just an x. The highest degree in my second term is also just an x. So we'll multiply those two together in order to get that my leading term is x squared. Again, you do not need to multiply all this out. You do not need to distribute it. This is not asking for standard form. So we just need to find the highest degree term or the leading term. And so that has a degree of 2. So that's telling me it's positive. So that means my right side is going up. And it's also even. So that means my left side is matching my right. Okay, so the limit as x approaches negative infinity. So as we're going to the left, our graph is going up. So it's approaching infinity. And as we're going to the right, as x approaches infinity, our graph is again going up. It approaches infinity. Okay. And so that's going to be our end behavior so far. So now let's talk about zeros and turning points of polynomial functions. So polynomial function f of degree n greater than 1 has at most n distinct real zeros and at most n minus 1 turning points. Okay, so a multiplicity is a zero that occurs more than once. So basically what this definition is saying is we could have n real zeros of any graph. We could have less than that, but we could at most have n. And again, in our graph, we could have at most n minus 1 turning points. So multiplicity is when we have something that occurs more than once. And if we have an even multiplicity, that means that our graph is tangent to the x-axis, otherwise known as bouncing. It bounces. So that looks something like, yes, it would bounce. That's an example of a multiplicity. Or if it's an odd multiplicity, then the graph crosses the x-axis. Okay, and what that looks like is instead of just being a line, because that's what happens when you just have something to like the first power, because this is a multiplicity, it's going to look a little more like approaching, flattening out, and then keep going. That's what a odd multiplicity looks a little bit more like. Okay, so if we have this function, okay, so f of x, so n is the highest degree. So the highest degree here is 6. So for this function, then it has at most 6 distinct real zeros, and it would have at most 6 minus 1, so 5 turning points. Okay, and so we have that graph, it's given to us right here. And the number of zeros we should hopefully see is we have 1, we have 2, and we have 3. So we actually have 3 zeros seen here. And the number of turning points are where our graph changes direction. So our graph is changing direction down here. It's changing direction right here. And it's changing direction again down here. So that's 3 turning points. So this again could have at most 6 distinct real zeros. It only has 3, or at most 5 turning points. It only has 3. So remember that at most does not mean the function has to have that many zeros or turning points. The function can have up to that amount. And that can change due to imaginary zeros and multiplicities, things like that. So just be careful with that. So remember that zeros are another way of saying solution or roots or x-intercepts. All of those are another way to say zeros. So looking at number 8, we want to state the number of possible real zeros and turning points of the following functions, then determine all the real zeros by factoring. So we are going to go back to factoring, so just be really, really careful with that one. So again, the possible number of zeros, we have this exponent of 4. So there is 4 possible real zeros. 4 minus 1, that'll give us 3 possible turning points. Okay, so if we want to factor, we have 3 terms here. So that's typically a hint that we're going to use the box. We can't take out a greatest common factor. So I'll put x to the 4th here, 3 here. So we want something to multiply to 3x to the 4th, but add to that middle term of a negative 4x squared. So that's going to give us negative x and a negative 3x squared. Sorry. I know that's hard to see. I'm going to zoom in a little so we can see it a little better. And so I can write a little smaller. Okay, so negative x squared and negative 3x squared would be those two numbers. So out of the first column, the two factors, or the greatest common factor is x squared. Out of the second column, the greatest common factor is 3. Out of the first row, the greatest common factor is x squared. And out of that last row, the greatest common factor is going to be negative 1. So this factors to x squared minus 1, x squared minus 3. But again, remember to find those zeros. We set it equal to 0. And both of these, we can do a difference of squares. So for the first one, the square root of the first term is x. The square root of the second is a positive 1. So we do square root of the first plus square root of the second, square root of the first minus the square root of the second. And we can do it again for this other factor. It would just be x plus radical 3 and x minus radical 3. From there, we would set each of those zeros equal, or each of those factors equal to 0 and solve. And when we did that, we'll get that x equals negative 1, x equals a positive 1, x equals a negative radical 3, and x equals a positive radical 3. So our zeros are going to be plus or minus 1 and plus or minus radical 3. Okay, so in that case, we did have the total 4 real zeros. So looking at number 9, the most possible number of zeros we can have is 4. Again, the possible number of turning points would be that number minus 1, which is 3. And again, we want to factor. So this one's actually a little nice because it has a greatest common factor. That's going to be x squared. So that'll leave us with x squared plus 5x plus 6. So again, we're going to use that box. So we'd have x squared and 6. So we want something to multiply to 6x squared, but add to 5x. So that's going to be 3x and 2x. So our factors would become x plus 2, x plus 3. So we set this up as x squared, we can't drop that, times x plus 2, times x plus 3. And again, we'll keep that equal to 0. And we'll set each of those factors equal to 0. So we do need to set that x squared equal to 0, that x plus 2 equal to 0, and that x plus 3 equal to 0. And so when we solve that, we should get 0, negative 2, and a negative 3. So 0, negative 2, negative 3. Okay, and then one thing we should hopefully notice is, see how we have this x squared? So what that means is when we solve that, if we could actually solve that twice by saying x equals 0 and x equals 0, right? Because it's x squared. So we can set each of those individual x's equal to 0. And so that is a multiplicity. So 0 is actually a multiplicity of 2 because the root of 0 is actually happening twice here. Okay, so that's how we'd write that. 0 mult 2 because it's happening twice. So if I had like x plus 2 squared, then that negative 2 would have a multiplicity of 2 as well, because that 0 is occurring twice. So just need to be careful with that. Again, if I had maybe x plus 3 to the fourth, that would be root negative 3 molt 4, because it's happening 4 times. And so that's how we would write that. So looking at the next one, the number of possible zeros is that highest degree, which is 3, and the number of possible turning points is going to be 2. Okay, we have 4 terms here, so we're going to use the box again. So we'll have x to the third. Again, there's no greatest common factor here. 18, and we'll fill in the other 2 boxes, negative 2x squared and a negative 9x. So we can take out x and negative 2 and x squared and a negative 9. So we'll get x minus 2, x squared minus 9. That second one is a difference of squares. The square root of the first term is x. The square root of the second is 3. So we do x plus 3, x minus 3. And again, put it all equal to 0. So we get that x equals 2, x equals a negative 3, and x equals a positive 3. So 2 and plus or minus 3. No multiplicities here. Okay. So next section, determine whether each graph could show a polynomial function, write yes or no. If not, explain your answer. So polynomial functions are continuous with no sharp turns. So the first one would be no, and the reason it's not is because it's not continuous. Right? The graph has this big blank here and this big blank here. These graphs are not meeting up, and so therefore it's not continuous. The second one is yes. Oops, sorry, pen just went on the fritz. Yeah. The second one is yes, there are no sharp turns. The graph is continuous. It never stops. And so therefore that one would be a polynomial function. Number 13 is no, and while it is continuous, it's not stopping. It has this sharp turn right here at 1. So it has a sharp turn at x equals 1, right? It's making this V shape. And so because of that, if that was a curve instead of a turn, this would be continuous, but because it is that sharp turn, it's going to be no. And then finally, this says use the end behavior of the polynomial graph to determine if the leading coefficient is positive or negative, and if the degree of the polynomial is odd or even. Okay, so in this first one, we have our right side is going down. What's happening here? And our left side is going up. So remember that right side going down is meaning it is negative, and the left side doing the opposite of the right means it's going to be odd. Okay. In our second one, we have the right side is going up and the left side is going down. So again, that right side going up is telling us that it is going to be positive. That leading coefficient is positive. And again, the left side is doing the opposite of the right. So it's going to be an odd degree because it's doing the opposite. And finally, the last one, we have our right side going up and our left side doing the same. So because our right side is going up, that means that we have a positive leading coefficient. And because our left side is matching our right, it's going to be an even degree. Okay, and so that should finish out the first set of notes. So do the best you can on the homework. Get as far as you possibly can. I know I'm not in class, but hopefully that is good. Okay, bye guys, have a good day.